Hi, today I am going to discuss about turn on and turn off methods of thyristors. Last class we have discussed about two transistor model of thyristor. There we have seen that if anyhow we can increase the current gain of two transistors alpha 1 and alpha 2 close to unity, then thyristor will be turned on. Ultimately, to turn on the thyristor, junction J2 is to be breakdown. Based on that one, today we will discuss some methods. Those are known as turn on and turn off methods of thyristors. So, turn on methods of thyristors. As we know that a thyristor can be turned on by breaking the junction J2. The junction J2 breaks down because of crossing the majority carriers from P to N and N to P. It may be because of anode to cathode voltage applied across the thyristor or because of gate current applied across the thyristor. But there are other methods also which can break this junction J2. Let's see those methods. Thermal method. This is also known as thermal triggering of thyristor. If temperature of the thyristor because of any reason increases, it may be because of increasing environmental temperature or because of heating effect of the nearby devices placed across the thyristor, junction J2 will break down. Because of the increase of temperature, as these four layers are made up of semiconductor material, so with the increase of temperature, more number of carriers will develop. Number of free carriers from the outer orbit will be liberated and will try to cross the junctions. So the depletion layer of the junctions will reduce. Ultimately, if further temperature increases or because of the repulsion of the charges, these junctions will break down and thyristor will conduct. This phenomena can be represented as increase in current gain of two transistors, alpha 1 and alpha 2. And in case alpha 1 plus alpha 2 is close to unity, or anyhow if the anode current is more than the latching current, then the thyristor will be turned on. But this method is generally not preferred because the instant of triggering is not available. It is very complex triggering method, so it is not generally preferred. Next, light triggering. If light is allowed to strike on junction J2, just like phototransistor, because of the bombardment of light on junction J2, more number of carriers will be liberated. And these carriers, just like thermal triggering, will try to cross the junction and will reduce the potential barrier. Ultimately, alpha 1 and alpha 2 will increase and thyristor will turn on. This kind of method is generally preferred whenever isolation between driver circuit and power circuit is required. And this kind of thyristors are known as photothyristors. Next method, high voltage triggering. In VI characteristics of thyristor, we have seen that if anode to cathode voltage is increased more than the forward breakover voltage, I have represented that one that by VBU, then the thyristor will be turned on. But in this method, the turn on voltage required, or you can say anode to cathode voltage requirement, is very high, so it is also not preferred. Instead, thyristor is to be protected from this high voltage triggering. Next is DVDT. If rate of change of voltage across the junction J2 is very high, this generally occurs at the instant when supply voltage is connected across anode to cathode. Without any gate supply, there may be the situation that DVDT across junction J2 is very high, and the junction J2 is nothing but it behaves like a capacitor. So if DVDT across the capacitor is more, then junction J2 will break down and thyristor will go into conduction state. This method is generally not preferred and protection is developed across the thyristor to protect it from high DVDT. Next method, gate current. We know that if a positive gate current is applied across junction J2, then because of that positive supply voltage, it will attract electrons towards itself and will be attracted towards cathode as well as gate. So junction J2 will break down. And if anode is connected to positive supply and cathode to the negative supply, then already junction J1 and J3 were forward bias. So now by application of positive gate current, junction J2 breaks down, J1 J3 was forward bias. So ultimately 4 layers are flooded with carriers, and easily the electrons are attracted by the anode and holes by cathode, and current will flow from anode to cathode. That means thyristor is now completely on. So in these methods we have seen that anyhow we have to break the junction J2 and anode current must be more than the latching current. Then we can say our thyristor is on. Out of these methods, thermal, light, high voltage, DVDT and gate current method, most favorable or preferred method is gate current method. Next, whenever isolation is required between driver circuit and power circuit, then photothyristor's are suitable. Now let's verify this gate current method. In this diagram, we want to show that if gate current is increased, then anode to cathode voltage requirement to turn on the thyristor is reduced. Let's start with the gate current 0. The extreme right hand side you can see Ig equal to 0. So at this current, anode to cathode voltage requirement is VBU, that is forward breakover voltage, to turn on the thyristor. Now let's increase the gate current slowly. Now at Ig1, as the gate current is increased, so the voltage requirement to turn on the thyristor, now you can say it is reduced. You can plot that one along VAK axis, anode to cathode voltage axis. Further, if gate current is increased to Ig2, then further anode to cathode voltage requirement to turn on the thyristor is reduced. So we can see here that if gate current we are increasing, then anode to cathode voltage required to turn on the thyristor is reducing. So it is obviously best method, because at low voltage and low current we can turn on the thyristor. So that is the most preferred and the suitable method to turn on the thyristor. Characteristics of thyristor. Let's see. Here in this diagram, two currents are shown, anode current and the gate current. Top one graph is for anode current and the bottom one is for gate current. Now we can see that gate current starts from 0 and reaches to final value, or you can say here steady state value. But at the same time we can see that anode current does not start at the time gate current is given. After some time anode current starts building. The reason behind it is that as soon as gate current is applied, carriers starts moving in the opposite directions, or you can say electrons moving towards the anode and holes towards the cathode. At the same time, three junctions is to be break down. This takes some time. Because of that one, this delay time is there. Here two currents are drawn, delay time and the second one is the rise time. So delay time is that when the gate current increases from 10% of Ig to achieve 10% of the rated anode current. So the duration is known as delay time. Now after 10% of anode current, when anode current reaches 90% of Ia, 0.9 Ia, we can say our thyristor is completely on, or it has achieved value more than the latching current. During this duration, the gate current will achieve 90% of the Ig. So in representation we can say the turn on time of thyristor is equal to delay time plus rise time. Delay time is the time between the duration when gate current starts from 10% of Ig to 10% of Ia. So this is the delay time, and the rise time is from 10% of Ia to 90% of Ia, and the total turn on time is equal to Td plus Tr. Now to reduce this delay time as well as to reduce the rise time, in designing the thyristor, different doping levels of p-n and type materials is used. If the doping level is increased, then obviously its rise time as well as delay time will reduce. Then in that case the thyristor can be used for high frequency applications. High frequency means very low turn on and very low turn off time. So let's see about the turn off time. Once the thyristor is on, now to make the thyristor off, there are different ways to turn off the thyristors. First one, you can increase the load impedance so that current or anode current will reduce less than the holding current, then the thyristor will be off. Then to turn it again, you have to apply again a positive gate current, and anode must be connected to positive and cathode must be connected to negative supply. Second is that in case of AC supply, we know that in positive half cycle, positive magnitude voltage is available, and in negative half cycle, negative magnitude voltage is available. So automatically, voltage across anode and cathode is changed. In positive half cycle, anode is connected to positive supply, cathode to negative supply, and in negative half cycle, anode is connected to negative supply and cathode to positive supply. So when reverse voltage is applied in the negative half cycle, then automatically these carriers will try to move in the opposite directions and the junction will build up. After recombination, thyristor will be completely turned off. Now this process can also be divided into two parts. First part is when all the conducting carriers are swept out or recombined to rebuild the three junctions. The turn off duration can be split in two parts. First part is the duration during which the carriers moves in the opposite direction, and this duration is known as reverse recovery time. During this time, junction J1 and J3 is built up. Second part is the duration during which the carriers recombined to build the junction J3, and this duration is known as recombination time. The first part, or you can say the reverse recovery time, depends upon the magnitude of the reverse voltage applied. If the reverse voltage applied is very high, then quickly the junction J1 and J3 will build up, as well as so turn off time is reduced, TRR is reduced. The second part is the current almost dies out due to leakage current. So second part is related to recombination process. During this recombination process, very small amount of current, or you can say leakage current, flows through the circuit, and this current we can neglect, and all the carriers are swept away to rebuild the three junctions. So when all the three junctions are built up, then again we can turn on the thyristor in the positive half cycle. Let's see the simulated waveform of this process. See, here three plots: input voltage, gate current, and anode current waveforms are shown. Top one is the input voltage. Input voltage from 0 to pi it is positive, pi to 2 pi it is negative, likewise it will continue. Now at any instant, gate current is applied across the thyristor. Because of that gate current, as in the positive half cycle, anode is connected to positive supply and cathode connected to negative supply. So when gate current is available, thyristor will be on. Now the thyristor will remain on till all the carriers are removed from the system and junctions build up. Now you can see at pi, though the input voltage becomes 0, but still the third waveform, anode current is there in the system, and that anode current is -1. This negative current is because of the reverse voltage applied from pi to 2 pi move in the opposite directions. As the carriers moving in the opposite direction, so the current is negative. Now the reverse recovery time is the time during all the carriers reaches to the initial position. That means in the 4 layers PN. Now the recombination process will start. Though free carriers is still available across the system. Now these carriers, as they have traveled, now there are no free carriers movement, or very small amount of carriers are moving, so we can neglect that one. So majority of the carriers traveled back to the initial positions PN. So the duration during which the carriers move in the opposite directions is known as reverse recovery time, and this time is very important one. This should not be neglected, because in this duration current may achieve very high value. Now after reverse recovery time, when the carriers moved back in the initial layers, then the carriers will recombine each other to settle down and to build up all the three junctions. So this duration is known as recombination time. During this recombination time, the current is almost zero. After that, all the junctions completely build up and thyristor is ready to again turn on. So the turn off time is equal to reverse recovery time plus recombination time. Second gate pulse is given when the input voltage becomes positive, then the thyristor will again turn on and it will follow the same process. So today we have seen just basics of turn on and turn off methods of thyristors. Different methods we have seen: thermal triggering, light triggering, deviated triggering, high voltage triggering, gate triggering. And for turn off, we have seen that anyhow we have to reduce the current less than the holding current, and we have to allow some time to settle down the excess carriers, or we have to sweep away all the carriers and recombination period. That is all about turn on and turn off methods of thyristors. Thank you.